So just as a reminder, when the paths that are followed between sets of points can be continuous, and that would be a line, that would be continuous. This would be continuous. And the book kind of describes this as like following a road rather than following stepping stones and jumping. So in other words, there's this concept of there are points right next to each other, creating a line. All right, so now let's talk about something else regarding sets, and that's the intersection and union of sets. We know that sets are named with uppercase letters and sets contain elements. So if there are some elements that are common or belong to two different sets, that is considered the intersection of two sets, and that is the intersection symbol. So let's look at an example. So here I have set A has the elements 1, 2, 3, 4, and set B has the elements 2, 4, 6, 8. And we want to find the intersection, and then also we want to find the number of elements in the intersection. So set A intersects with set B. It's going to be a set. So 1, is 1 in B? No. 2, is 2 in set B? Yes. So it would be considered in the intersection. Is 3 in set B? No. Is the number 4 or the element 4 in set B? Yes. So the intersection of set A and B is the set with the numbers 2 and 4 in it. And so what is the number, or how many elements are in A intersect B? 1, 2. There are 2 elements in that intersection. Now, if sets do not have any elements in common, their intersection is called the empty set. The empty set, that's a set that has no elements. You can write the empty set like that. All right, so there's a set with no elements. Or you can write the empty set like that. Do not do this, though. That is not correct. That is not the empty set. That is a set that has one element. So that is not correct. And if two sets have no elements in common, they're called disjoint. Now let's talk about union. The set of all the elements in either set 1 or set 2 is called the union of the sets. And this is the union symbol. It kind of looks like the U in the word union. All right, so let's have an example here. If I had set A was the numbers 1, 2, 3, 4, 5, and 6. And then I had set B were the numbers 2, 4, 6, 8, and 10. What would A intersect B equal? Is 1 in both? No. Is 2 in both? Yes. Is 3 in both sets? No. Is 4 in both sets? Yes. Is 5 in both sets? No. Is 6 in both sets? Yes. So A intersect B would be that set, and the number of elements in A intersect B would be 3. But what would A union B look like? Those are all the elements in either set A or set B. So we're going to have everything that's in set A. 1, 2, 3, 4, 5, 6, and now we're going to go through set B. Is 2 already in there? Yes, we don't need to enter it twice. Is 4 already in there? Yes. Is 6 already represented? Yes. Is 8 all represented? No. So we're going to add 8 into the union. And is 10 already represented? No. So we're going to add 10. And so how many elements are in A union B? 1, 2, 3, 4, 5, 6, 7, 8. There would be 8 elements. And then sometimes sets are represented as Venn diagrams. So this is a construct that uses circles to represent sets, and they're called Venn diagrams after John Venn. So let's take a look here. We already know, we've already seen these symbols for subset, intersection, intersection, and basically equivalent sets. Here we see that subset A, the circle A, any element that is in A is also in B. So set A is a subset of B. The entire circle is encased. The entire circle for set A is encased in B. If A intersect B is not empty, in other words, they have some elements in common, we'd represent them separately, but the elements that are in common would be in that overlapping parts of the circle. And here we have disjoint sets A and B. In other words, their intersection is the empty set. They're totally separate, no elements in common. And then if A and B are equivalent sets, we would have a single circle, and A, it would have the two names in it, both A and B in there. So what about that phrase equivalent? If two sets have exactly the same elements, they are equivalent. Remember, order is not important in a set. Either an element is in a set or it's not. So if we had set E, which had the numbers 2, 4, 6, 8, and we had set F, which were all the even numbers between 1 and 9, so that would be 2, 4, 6, and 8. These are equivalent sets. All right, so let's do some examples of our diagrams here. Or some examples of relationships here. So we want to know if it's a subset, an intersection, a disjoint, or if they're equivalent. If set A are the numbers 1, 2, 3, and B are the counting numbers less than 4, so B would be 1, 2, 3, and then we're going to stop because it's less than 4. Look at set A and set B. You know what? They are equivalent. Equivalent. Let's look at B here. Set C is 2, 4, 6, 8, and D is all even numbers, so that's going to be like negative 2, 0, 2, 4, 6, 8, 10. And in fact, this goes to infinity in the negative numbers and the positive numbers. Since every element in C is also in D, we would say that C is a subset of D. All right, let's look at set E here. 2, 3, 5, 7, and 11. And then F are the single-digit counting numbers. So that would be 1, 2, 3, 4, 5, 6, 7, 8, and 9. Well, they're not equivalent. They're not subset, because here there's an 11 that's not in my set F. But what we could do, we would say the intersection of E and F is 2 is in there, 3 is in there, 5 is also in F, and 7 is also in F. So we could say 2, 3, 5, and 7 are the intersection. And then let's look at D. All the even numbers, and set H are all the odd numbers. Well, there's absolutely no there's no overlap. So the intersection of G and H, there is no overlap. We would say those two sets are disjoint. All right, let's look again at some polygons here. And here, the term universe describes all the sets that contain all the elements and all the subsets that you're going to consider. So here, we usually draw a box around our universe. And here, we're going to call that the universe is all the dogs. And here we have subset P, that might be all your Pomeranians. Here's my subset C, those are all your collies. Here's subset B, those are all your beagles.